The next talk will be by Emily Costello, Impact Gardening of Ancient Ice on the Moon.
All right, thanks so much. All right, so today I'm going to be sharing some of the results of a recent publication. Got this paper into JGR Planets earlier this year. And it's a pretty big paper. We cover a lot of topics about impact gardening and its effects on ice on both the moon and Mercury. But today I'll just be focusing on the results that we got from impact gardening of ancient ice on the moon. So impact gardening is the process by which small, frequent impacts churn the uppermost surface of the moon. We're looking at an Apollo core here from Apollo 16, where the tick scale is centimeters. And we can see evidence of impact gardening in this core, where on the left, this area was closer to the surface, and on the right, further from the surface. This gradient of darker material to lighter material is the evidence of impact gardening, where space-weathered material has been churned and worked to depth, much greater than it could have been produced at. I have a model that describes the depth of this impact gardening zone as a function of time. The parameters that I put into the model are a cratering rate and some Poisson statistics. The evidence of impact gardening from the Apollo cores is presented in this plot, where we can see these yellow squares and triangles. On the horizontal axis, we're looking at the amount of time that's implied by the mixing. And on the vertical axis, we're looking at the depth of that impact garden zone. The solid line is the results of the impact gardening model using the observed production rate of splotches. These are albedo anomalies that were observed in temporal pairs by the Lunar Reconnaissance Orbiter camera team and published by Spire et al. In 2016. Now, the dotted blue line is a completely theoretical production where I've put in a model of the flux of secondary impacts that includes assumptions about how many secondaries are produced per primary impactor, how many, the velocity of those secondaries, the material properties of the surface regolith, including yield strength, porosity, and density, and also the density of the impactor itself. Now, my completely theoretical model that includes all these assumptions about secondaries and material properties fits the model that used those observational cratering rates and the depth of gardening implied by the Apollo cores. Now, here's another perspective of the impact gardening results in regolith, where I've flipped the vertical axis, where we're still looking at gardening depth, but we have the surface at the very top and we're proceeding to depth, digging deeper as we go down. The horizontal axis is probability. Now, we can think about probability here. If you're familiar with crater statistics, you can think about 100% or approaching 100% probability as crater saturation at these gardening depths. And at lower probabilities, we're at crater sizes and crater depths that are approaching saturation but haven't reached it. And due to the stochastic nature of these impacts, there's some probability the region will see more impacts and deeper gardening than is implied by that 99% saturation gardening, thorough reworking. Now, there's some evidence that there are ancient ice deposits on the moon buried below possibly meters of regolith. Paul talked about this earlier, that Lior Rubinenko in 2019 showed that there are craters at the poles that are shallower in their depth diameter than other craters that are away from the poles. And he proposed that there may be a lens of ancient ice buried below the regolith. Ariel Deutsch also showed that these craters that have ice in them, the permanently shadowed region ice, are ancient, older than Copernican. Well, my impact gardening model shows that over the last billion years, impact gardening at lower probabilities has been upsampling that buried ice. And it's possible that impact gardening upsampling, these larger, rare impacts, could explain the present day patchy surface ice that we see. This is good news for ISRU. It means that even if the ice is buried 3 meters deep, it's still being upsampled by impact processes over relatively recent timescales, and it may be sampleable and more accessible to us. But I also want to understand how that ice got there initially. There's something that kind of bugs me about this idea of a thick layer of regolith over an ice lens. How did that regolith get there? I always point to the pyroclastic deposits, which are supposedly about the same age, billions of years old, but they're still spectrally distinct at the surface. They haven't been covered by a layer of regolith. So what if instead we had an exposed ice deposit that was exposed to impact gardening over time? What would happen to that deposit? And I can explore using my model how thick that ice deposit must have been initially to have been gardened away to its current state today. So to start, I'm going to model impact gardening in an icy target. Here we're looking at a plot of impact gardening as a function of time again. And the white lines are impact gardening in regolith, and the pink and yellow lines are impact gardening in a hard ice target. I've taken that theoretical model and I've plugged in material properties for an icy target to get these calculations. Now, the flux that I use is only valid over the past billion years, and the ancient flux was much higher. So to anchor our gardening calculations, we anchor on the thickness of the mare regolith. Assuming that 99% probability, 10 reworking events have created a 3-meter thick mare regolith over 3.5 billion years. I can then scale my calculations of impact gardening in an icy target up appropriately. And I find that an ancient deposit must have been about 10 meters thick. If an ancient ice deposit was 10 meters thick, then gardening of that deposit would have pulverized it and mixed it with underlying regolith. This thickness of 10 meters is similar to the thickness or the order of magnitude of the thickness of Mercury's ice deposits. And it's also similar to the thickness that was proposed by Deborah Needham in 2019 from a volcanic source that may have been ancient. Now, in conclusion, I've been able to show that the moon may have once had Mercury-like extensive ice deposits that were about 10 meters thick, that have been pulverized and churned into underlying regolith over the past 3.5 billion years or so by impact gardening. I also showed some hope for ISRU that the remains of any ancient ice that may reside well below the reach of present neutron spectrometer and radar observations are continuously presented to the surface by stochastic impact gardening. If you want to see more about this model or any of our other conclusions about ice on the moon and Mercury, I've included the reference here for your further exploration. Thanks so much.
Hi, Emily. Thank you very much. We have time for some questions. I have one, but I'm waiting for some to show up on chat or a hands be raised. But while waiting for that, can you give some insight onto, in the gardening, how isotropic it would be due to this process, or do we expect things to be uniformly mixed or not?
So I think that we can kind of capture that with the probability. Like I said, the higher probabilities are crater saturation. That is that every point on the surface has been influenced by a cratering event. And I would say that that's pretty well mixed. If we look back at the Apollo cores too, we see a really well mixed zone of space weathering products to about 10 centimeters depth in the right time period. So I would say it's pretty well mixed.
Okay, thank you.
Yeah.
We have another minute till we need to move to the next talk, so stay on schedule. Just wait about 30 seconds or so.
Okay.
I think we have a question on the chat, Emily, which is whether you've considered the moon's obliquity and how that might have changed over the past 3.5 billion years.
Well, that's really interesting. I haven't included that. Does this person asking the question mean that there would be a change in the impact flux implied by the obliquity?
No, just that the moon may have wobbled around, and so if it wasn't placed at the poles 3.5 billion years ago, the pole might not be there anymore.
Right, that's a great point. my model is pretty simplistic. I'm just throwing rocks at the moon basically, and whatever is there, I'm hitting. So if the moon had some wobble, and if these ice deposits were thicker to begin with, and were eroded by obliquity and sublimation processes, then that gives us a bigger budget initially of ice. So if we had more water delivered, we could have more removed, but impact gardening could destroy a 10-meter thick deposit over the past 3.5 billion years.
Okay, thank you, Emily. Very, very nice talk.